For about the last 10 years, my laboratory has been studying heat shock protein 27, or I'll refer to it as HSP 27, as a factor that reduces hardening of the arteries, and also a protein that you can measure in the blood and serves as a biomarker or predictive of cardiovascular events. There are many heat shock proteins, and the classification is a little bit confusing. Some of it is based on size of the protein. They've also, a number of people in this area have come up with different names for these kind of proteins, but they're very interesting, and they're common in whether you take a sauna and increase your body temperature, or if you're a frog and you freeze under the ice in the winter, something has to control the proteins in there so that they don't completely gel up. Essentially what we're focusing on is trying to understand more completely the mechanisms involved in the development of hardening of the arteries, as well as the progression of hardening of the arteries. And our focus is currently based a lot on what happens to cholesterol levels. And so we have new information about how this protein may reduce cholesterol buildup not only in the blood, but also in the plaque, like in the artery wall. It reduces hardening of the arteries, and it reduces cholesterol in the arteries, as well as cholesterol in your blood. Hardening of the arteries causes heart attacks and strokes, as well as other blood vessel disorders, and it's the number one killer in the Western world. That's exactly what we're trying to do, to develop a new therapeutic. And the interesting thing about this is we're studying a protein that your body normally makes, and what we're trying to do are find ways to either deliver replacement therapy or to increase the circulation time of the protein in your blood, or increase its potency. And we have developed some strategies for both of those. We've made the protein using bacteria as factories, and so we can make large quantities of the protein, and we can chop up the protein into smaller fragments and then deliver it as a therapeutic, for example, under the skin with a small injection. But we've also found ways by immunizing to create almost like a vaccine to increase the half-life of the protein that exists in your body. This is particularly important for people who are at risk for heart disease, but where this all came from, and where this is particularly interesting, is where women, as they go through menopause, will be at more risk for developing hardening of the arteries. And what we were originally studying were ovarian hormones like estrogens, and it just so happens that this heat shock protein, the abundance of the protein is in part regulated by ovarian function, particularly estrogens. So in an animal model, for example, if you removed the ovaries, the heat shock proteins would stay very low, and you would lose protection against atherosclerosis. What we could be developing is a replacement therapy where we administer the protein or a fragment of the protein. It could also be a situation where we just give a part of the protein and what are called adjuvants to increase the immune response and build up more antibodies, which in fact are helpful antibodies. They're not antibodies that squelch the protein, they're actually antibodies that potentiate things. And of course we could do both, give the protein and immunize at the same time.